Well, good morning. It is Tuesday. We're making it through this last week. What is today? March the 16th. Okay, so to start the class today, we ended up working, students just worked through 7 through 11. And so now let's just kind of go over and see what we got and see if we know what to do. So those of you watching at home, pause the video and see if you can do 7 through 11 on this sheet that I'm pretty sure I posted. If not, I'll double check and make sure it's posted before you see this video. All right, so what is the molarity of an HCl solution if 22.5 milliliters of 0.15 molar neutralize 15 milliliters of the acid? How do I solve this? MAVA is equal to MV/VB. Okay? So the molarity of the acid times the volume of the acid, what does that give you? What does molarity times volume give you? Moles, right? So that's giving moles of acid equals moles of base. That's the equivalence point. That's the neutral point. That's when moles of acid equals moles of base. That's when the titration is finished. Okay? So the question is the molarity of the HCl, so that's what I'm looking for, is equal to the molarity of the base, which was given as 0.15 molar. Now the good news is, because this is a ratio, the volumes can be in any units again. It doesn't, you don't have to change it to liters. It won't hurt if you change it to liters, but you don't have to. Okay? Because if you divide each of them by 1,000, it's still going to be the same ratio. So I'm going to take the volume of the base is going to equal 22.5 milliliters divided by the volume of the acid, which was 15 milliliters. So this is a very easy, straightforward problem. And we end up getting how many? That's going to be just 0.1, so 2.25? No? 0.225. Oh yeah, 2 decimals. 0.225 molar. Okay? Now, what's different about number 8? Can I just use MAVA equals MBBB on number 8? That's what I did. Right? I thought I could. Look at it. What's different about number 8?
Oh, it has to be multiplied by 2.
So what?
It has to be multiplied by 2.
You have to, why?
Because there's 2 OHs.
There are 2 OHs here, right? And again, even though when you put it into water, this isn't real soluble, the acid pulls it into solution. Okay? So, when we do MAVA is equal to MBVB, okay, this is really not just moles of acid, it needs to be moles of H plus equal moles of OH minus. But when you have a dibasic substance like MgOH2, every mole of this that goes in, you're going to get 2 moles of OH that can be neutralized. So we're going to have to put a 2 out there in front of that one because we need moles of OH minus. Is everybody seeing that and understanding that? So we do everything else the same. The question asks for what volume, so we're going to be looking for volume of the base. So I'm just going to bring the 2 MV to the bottom over here. So I'm going to have the molarity of the acid is 0.125. The volume of the acid is equal to 35 milliliters. Divided by 2 times the molarity of the base, which is 0.1. And that's going to equal the volume of the base. Which means we're going to probably have to use half of what you thought you needed to use. What does that come out to? Say it loud up in here.
21.875.
21, so let's go to 3 sig figs, 21.875, so 21.9. All right, now using that same concept then, what about number 9? What are we gonna have to do with number 9? 2 H's, so where's the 2 go? It's H2SO4, right? So I'm gonna need, because I want moles of H plus, so each mole of H2SO4 is gonna give me a 2. So for number 9, it's gonna be 2 MaBa is equal to MbBb. Then you just plug in everything in. And what's the question? What the molarity of the base? What did we get for the molarity of the base? After you divide by 2. We just plug everything in, all those numbers in. What do you get? Everybody's redoing it? Point 2. Okay, so we should again have 3 significant figures to come out to 0.200. Does everybody see why we need the 2? We're all good? So you just gotta pay. Now I will tell you that 99% of the time, it's monoprotic, monobasic, it's just MaBa equals MbBb. Especially when you're doing a titration curve like we're about to look at and the different things, okay? So, but you just gotta pay attention if it's, and we call it if it has 2 or 3 OHs, it would be dibasic. If it had 3, we call it tribasic, meaning that's how many hydroxides it has, versus monoprotic, diprotic, triprotic, how many hydrogens it has. Just for terminology purposes, just so you can understand what it's saying. Okay? Total side note is just sometimes you can see you have the phosphate ion, you have monohydrogen phosphate, dihydrogen phosphate. So phosphate can accept 3 hydrogens to get to H3PO4. So it would be, sometimes they say, when I go and buy the chemicals, old school nomenclature, it'll be sodium phosphate tribasic. But if they said sodium phosphate dibasic, that means it's combining with monohydrogen phosphate, so it can only accept 2 more hydrogens. Or if it's sodium phosphate monobasic, that means it's going to be combining with the H2PO4 because it only can accept 1 more hydrogen. Okay, so sometimes you'll see that just in old school if you ever look at a chemical shelf. Maybe in the college you'll be a lab aide in a chemistry lab and you'll see all the different chemicals you're putting out there. But that's the only time you would ever need that. Okay, so number 10. What is the pH of a 0.15 molar sodium hypobromate solution? What type of substance is this? A salt, right? Which part, first off, is it acidic, basic, or neutral salt? How do you know amine is basic? The strong base, and this is a weak acid, so we know it's going to be a basic salt, right? So first off, I recognize this is a salt because it's just an ionic compound as a salt. It doesn't have a hydrogen or a hydroxide in it, okay? Now, if it's a basic salt, what ion is going to get produced? I heard somebody mumble it, OH minus. Okay? So what part of the NaBRO, the NaBRO compound, is going to react? To BRO minus. And what's it going to react with? BrO minus plus water. And we're gonna make HBrO plus OH minus. Okay? Now they give you, this is a base though, but they give you the Ka of this. Well, what do I need?
KB.
The Kb of that. So how do I find the Kb? Of BrO minus. And that all turns out to equal
4 times 10 to the negative 10.
So then what do I do with that? We want to do an ice table. What's my initial concentration? 0.15. 0 and 0. Change is minus x, x, and x. So I'm going to be, this. Now we're doing the exact same things we always do. We can go straight to the OH minus is equal to the square root of what?
4 times 10.
Okay, and I'm hearing all kinds of mumbling. You guys need to be bold. Speak up. They need to hear you on the camera. The world is waiting to hear your responses. All 80 people out there subscribing to my channel. Watching diligently each and every day, waiting, anticipating for another exciting chemistry video. And you know some of y'all go home and watch them just for fun. Yeah. What does this come out to?
7.75 times 10 to the negative 6.
So that's my OH minus concentration, but the question's asking for what is the pH. So what do I need to do now? The OH is equal to negative log 7.75 times 10 to the minus 6. So then my POH is going to equal 5.11. Is that what I heard? Okay, so we just subtract, so 14 pH is equal to 8.89. Now, notice what type of salt did we say this was? Basic. So make sure that your pH comes out above 7. Does anybody have any questions on this one? This is just a pH of a salt question. Classic, you have to use the 1 times 10 to the minus 14th divided by Ka to get Kb. But once you have the Kb, then it's just a weak acid, weak base problem. But a lot of people in the past, a lot of students in the past have struggled writing these net ionic equations. So we're going to kind of keep practicing that today and tomorrow, writing these and making sure we know how things are going to react. All right? Questions? Going once? Going twice? I'm going to erase. You guys are so excited this morning. All right, last one. What is the ratio of sodium bicarbonate to carbonic acid? This is the buffer in blood. Is needed to make a buffer with a pH of 6.2. Okay? The Ka of H2CO3 is 4.3 times 10 to the minus 7. So if I'm going to make a buffer with these, what's the equation that I want to write? Do I go H2CO3 plus NaHCO3? What equation do I use? HCO3 minus plus H plus. That's what the Ka is telling me. It's the acid constant. How is the acid gonna dissociate, or in this case, ionize? Okay, so the Ka is given as 4.3 times 10 to the minus 7. Okay? So I need the ratio. The pH of 6.2. So what does the pH of 6.2 tell me? It's acidic.
It's
I heard somebody say it. It's the H plus concentration, so Ka, 4.3 times 10 to the minus 7 is equal to HCO3 minus times H plus all over H2CO3. So what's the question asking? Just wants this ratio, right? So what's the only thing I need to know in order to be able to find this ratio? H plus. So the pH gives me that H plus. Whenever you have the pH, you know the H plus, you know the OH minus. Okay, so 10 to the negative pH, which is negative 6.2, is equal to H plus, is equal to
6.31 times 10 to the negative 7.
okay, which would go right there. So I know then that 4.3 times 10 to the minus 7th divided by 6.31 times 10 to the minus 7th is equal to my HCO3 minus over H2CO3, which is equal to 0.68. Okay, pretty close to 0.6666 or 0.67, so it's about a 2 to 3 ratio. Yes.
So is this one that we could use the Henderson?
You did perfect. Yeah, okay. I was just gonna go there. So what does she ask? Can we use the Henderson-Hasselbalch equation, which is pH is equal to pKa plus the log of that HCO3 minus all over H2CO3. We know the pH. What does pKa mean again?
negative log.
The negative log of this. Okay? So you would just go pKa is going to equal what? So somebody take the negative log of this one. Oh, just 6.37. It's not going to count. Okay, so therefore, I'm going to subtract. The pH is given as 6.2, right?
Yeah.
So it's going to be 6.2 minus 6.37. Okay, it's going to equal negative, is equal to the log of my ratio. I don't feel like writing it out. So then how do I, so that's going to equal negative 1.7. So how do I find the ratio? 10 to the negative 0.17 is equal to my ratio, which is going to equal
0.676.
676 is the ratio then that it needs to combine. Okay? 676 is pretty darn close to 0.68. Okay? Either way, they're both, this equation's derived from this. We're just taking the negative log of both sides of this. Okay? Which is how we're getting this equation. Just so you know. Okay, so a lot of people think that this is easier to try to find that ratio and plug in because the ratio is right there. You 100% correct either way you want to go. I don't think any way is easier than the other. The only reason I tend to go this way is just because that's how we solve all of our other equilibrium problems. And it's just the exact same thing, I'm just solving for this ratio. Okay? But whatever one makes most sense to you is the one you can use, or should use. Okay? All right, good stuff. Let's go to some very old. I had more on here, which one did I want? Did we already do this one, this methylamine one? I think we did. We already did that one. I didn't do it in the other class, but I did it in this one. All right, never mind. All right, so now. Where did I put it? Today, we really need to focus in, and I will scan this and post it and put this into a classroom. But here's a titration curve. Now, it's important for us to understand that all of our titration curves are going to look like this. This is, when we're starting with an acid, titrating it with a base, in other words, we're adding the base. So notice the pH starts off here. Today what we're gonna do is we're gonna look at, we gotta know the pH at 4 places. At point A, at point C, at point D, and point E. Okay? But let's just look at this multiple choice question. On the basis of the pH curve, the pKa value, how do I find the pKa given something like this? At the half equivalence point. Somebody else tell me what's true at the half equivalence point. Moles of H X equals moles of X minus, which means that pH equals pKa. So I go, where is the half equivalence point? Which letter? C, halfway through. This is going to be your equivalence point, the middle of the vertical part. Every one is going to have a vertical part because we run out of the base that the acid is, we run out of the acid that the base is reacting with. And so all of a sudden the OH minus concentration is going up rapidly because the OH doesn't have anything to combine with anymore. And so there's always going to be the steep curve, and it's going to be the middle of that is your equivalence point. So the halfway, I call it the midpoint or the half equivalence point, it's going to be here. So if I come across right here, it's between 5 and 6, right? So I take the pKa, the negative log of that, okay? The pH is equal to the pKa, it tells me that. Which one's my answer? B, because it's closest to 5. Does everybody see that? That question is going to get asked over and over and over again. I'm going to show you with actual AP questions now as the day progresses. Okay, same curve based on the graph. Wish I could have both on here. Okay, so I want to know on the graph above which species is greatest concentration at point B. At point B, there's my reaction. So I have HX, OH minus, X minus, or water, HOH. Now, actually I don't think water is one of the choices because water obviously is going to be the most because it's all taking place in water, but as far as being produced, okay? At point B, Are we to the half equivalence point yet? So which one is greater, HX or X minus? Somebody over here, I heard someone over here, what did they say? HX, right? Because you're starting with HX, H plus X minus. So initially, at point A, we're way down here, it's a weak acid, so the fact that it's a weak acid means that the majority is here, very little is here. But as I start adding base, OH minus, what does that do to my equilibrium? Shifts it which way? As I start adding OH minus. Okay? You can think of it as plus OH minus and then it's going to make water, or I always think of it as plus OH minus making water here, which means the reaction is going to shift that way. Right? So, little by little, I'm getting more and more X minus. When does HX equal X minus? What point? We already said. At C, right? So therefore, any point between A and C, HX is going to be in greater concentration. At C, they're equal. What about between C and D? X minus is going to be greater. Now what about OH minus? What's happening to, between point A and D, what's happening to the OH minus as soon as you add it in? It's being used and combining with the H plus, right, to make water. So is the OH minus concentration going to be significant at all? No. Okay? Between points A and D. Now, at point D, what's left? Really just X minus at this point. Okay, the OH, at point D, the exact equivalence point, H plus equals OH minus, so they've completely neutralized. There will be a small amount of OH minus, but the one in greatest concentration is going to be the X minus. Okay, we no longer have any of this. The OH minus, again, got completely used up by the H plus at that equivalence point. That's right when they're equal to one another. So X minus is the greatest. So here, HX is greatest. Here, HX is greatest. Here, they're equal to one another. Here, X minus is greater. Till D, all you have is X minus. Now once you start going past D, now we're putting in excess strong base. Now what's the predominant? OH from the strong base, because remember when we have a mixture of a strong base and a weak base, we ignore the weak base and just take the OH from the strong base. Okay? So, at point B, the answer is going to be HX.
I was gonna ask, it might be stupid, but with titrations and with the curves and stuff, is it always gonna be adding a base or will it?
No, it could go the other way.
Okay.
So, as a matter of fact, that's my original. I think I was supposed to go make copies of that. Well, I'll make copies at the break, but we can start and look at this one. Now you will find that methylamine is a favorite base of these problems. Okay? A teacher wishes to determine the concentration of a solution of methylamine he found on the shelf in the storeroom and part of the label indicating the concentration missing. To do so, he titrated 50 milliliter sample of the methylamine with a 0.2 molar solution of HCl. The teacher used a pH meter to measure pH at various points during the titration and generated the following curve. So this is what it would look like if you start with a weak base and titrate it with a strong acid. Now how would I know, without it being told here, how would I know it's a weak base? pH is down here around 11. A strong base is going to be 13, 14. Okay? So we're starting here. So what's point B? Half equivalence point. What's going to be true there? Okay? POH equals PKB at that point. Notice you put the methylamine. What's the equation going to be for the reaction of the methylamine? What's the net ionic equation going to be for the methylamine plus HCl? CH3 NH2. Will the Cl be a factor? It's going to be a spectator ion, right? So it's going to be plus H plus. And what's that going to make? Okay? Now technically we have a plus Cl minus and a plus Cl minus because everything is going to be neutral. Okay? So that's your HCl, and then this is the methylammonium chloride salt that's being produced. But the chlorides are your spectator ions, so we don't include. They want the net ionic equation. All right, so write a balanced ionic equation for the reaction taking place. That's this. Next question says, using the information above and the titration curve, determine the initial concentration of the methylamine. How can I find out what my concentration of methylamine is here? Say that again? MAVA equals MBVB, right? We want do we know the molarity of the acid? Yes. Do I know the volume of the acid? Where do I get the volume of the acid used? What point? C, because that's the equivalence point. That's MAVA equals MBVB is only at the equivalence point. So I know, well, I'm going to assume that's right at 70. Okay, so I know the volume of the acid. Molarity of the base is what I'm looking for. I used 50 milliliters of the base, so I can get the molarity of the base. MAVA equals MBVB. But we need to know that the volume is always going to be at the equivalence point right here of the acid. All right, let's take a break, get refreshed, get fired up, and we'll come back and do some more.